Okay. So last week we looked at the derivative, and the usefulness of the derivative is it helps us to find the turning point. So last week we learned that if I want to find this point, or if I want to find this point, or if I want to find a point like this, these points, what they all have in common is the derivative. The slope of the tangent line is 0 here, here, and here. Come on, Bruce. That was last week. Anyways, one problem that we saw last week was that when we find these points, unless we have a graph, we don't know if the point is a maximum, we don't know if it's a minimum, or if it's neither of these. So this is where the second derivative comes in useful. Second derivative. Hang in there, Monica. What's wrong? Okay, so what is the second derivative? Correct, Sean. Sean is 100% right. Derivative of the derivative. In other words, you differentiate twice. I think I'll use Sean's words here. The derivative of the derivative of y. So basically we differentiate twice. Let's have a look at an example just to get us started. So here's a simple example to start with. Y equals 7 sine x. So first derivative will be 7 cos x, and then second derivative will be minus 7 sine x. Okay. Yeah. Okay, let's do another example before we move on. I'll give you a minute to try this one. Y equals log 2x cubed. Okay, take a minute. I want the second derivative here. Come on. Okay. You got answers? Got answers? Yeah. Come on. Okay. So first before I even start, I have to change this into y equals log 2 plus log x cubed. Y equals log 2 plus 3 log x. So that means dy dx equals 0 plus 3 over x. Or in other words, 3x minus 1. So the second derivative will be, minus 3x minus 2, which is minus 3 over x squared. Yeah. Okay, now that we have a couple of examples done, let's see the uses of this second derivative.
Can I ask a
Yeah.
What's the difference between LN and LOG?
Not really any difference. A lot of books would use the same for both LOG and LN. On the calculator there's a difference. If you're reading in maths books or online, they usually mean the same thing. But on your calculator you should just use LN then. Yes.
How can we find this way?
Oh, Jerry. Bring down the power and take 1 from the power. You remember this from last week? Last week. Last week is forgotten, is it? Yeah. You were so busy doing your physics essay, you forgot about math. Yes. Yes. Okay, let's have a look at how we can use the second derivative. Okay, so let's take something simple like a quadratic. I will say y equals ax squared plus bx plus c. So we know that the first derivative is equal to 2ax plus b, and the second derivative will equal 2a. That's y, that's x. Okay, let's draw this graph here where we put the derivative on the y-axis, its value. So let's see what's happening. Here the derivative is negative, less negative, less negative, 0 for this value of x, positive, 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 positive. Yeah? So if I was to graph this, I would go from the negative up to the positive. Let me draw that again. And this point here, where it crosses the x-axis, that will match up exactly with this point. Because here, the derivative is 0. Now let's have a look at what the second derivative will look like. If I draw the second derivative, here the slope is positive, here positive, here positive. In fact, not only is it positive, but it's the same, which means if I graph it, be a horizontal line, yeah. Like this. Now let me just do all of this again, except put the graph upside down. So if my graph was upside down instead, like this, what would be the difference here in this graph? It would go the other way down, because here we're going positive first, 0, and then negative. So the graph will be upside down, and what would be the difference here? It'd be in the negative. That would be the only difference. Now, if you look at this, if this is the right way up, what do we know about the A? It's positive. If we look here, we're also saying if the A is positive, then this is positive, but of course at the very beginning it was positive. If this was this way, what are we saying about the A? We're saying it's negative, which it is. So in other words, the second derivative can tell us if the shape is like this or if it's like this. But the advantage is that it works for every curve. The problem with using the A here is it only works for quadratics. But now we have a way to know its shape for any curve by just looking at the second derivative. So just to put that in a little result box here. Oh, I should check actually, and maybe some people know the word. This shape has a name and this shape has a name. This one? U is fine. U is fine, but there is actually another word. Yeah, but both can be described using that word. So this one we call it convex, and this one we call concave. Okay, so the result is, if the second derivative is positive, then y is convex. If the second derivative is negative, the y is concave. Yeah. Can I scroll down a bit?
Yes.
Now, I didn't say it last time because it's something that we already know, but since we're putting results down, we might as well put this down as well. If the derivative is positive, that means the slope of the tangent is positive, like this. And if it was negative, the slope of the tangent is negative, which is like this. So if it's positive, then it means the y is increasing, because the slope is positive. But you knew this already, it's going up. And if negative, the y is decreasing. Yep. Yeah. Now, gets a bit interesting when they're zero. So we learned last time, it's interesting when this one, is that the door? No. It's interesting when this one is zero. What happens when this one's zero? We can find the turning point. So, just an aside here, if dy dx equals 0, then that means we have found a stationary point. Yeah? Now, I'll just give you a minute to think about this before I ask you. But think about what it might mean if this one, the second derivative, is 0. Think about what it might mean. I'll just give you a second. Okay, got that?
Yes.
So, who thinks they can tell me what it might mean? Y is 0? Not this.
No, linear.
Not linear.
The second.
Go on, Sean.
You mean find the next moment.
Well, my question was, what does it mean if the second derivative is 0? Anybody can picture what this might mean? No. No. Yes, Sean.
I know this
Go on.
Chinese name, but I don't know English.
Try your best.
It's if the first derivative and the second derivative both equal 0, that means yes, I know that.
Now, I didn't say anything about the first derivative, though. The first derivative, we don't know. I'm just telling you the second derivative is 0. If the second derivative is 0, then we have something which is called an inflection point. Yeah? What is an inflection point? Let me show you on the graph over here. What shape is this? Convex or concave?
Concave.
Concave. So its second derivative is negative. And what shape is this? Convex, and its second derivative is positive. But here, where these two shapes meet, this point here, everything here is concave. And everything here, every point here is part of a curve which is convex. And every point here is part of the curve which is concave. But this point right here, it's the point between the two where it switches from being concave and convex. This is where the switch happens. And this point is called the inflection point. Okay, you got that? Not yet? Okay. Continue, do you have that yet? No? Yes? Yes, okay. So we're doing a lot of theory. We'll get to some examples now in a moment, but just before we can continue, I just really want to point out the direction of this arrow. Okay, this is not this way. What I mean by that is, if the second derivative is 0, then we have an inflection point. But we could have an inflection point where the second derivative isn't 0. So my point is, it's one direction only. This means we have an inflection point, but just because we have an inflection point doesn't mean that this will be true. So the direction is one way only, and that's actually very important to note, that it's one direction only. So you could have a situation where you have an inflection point and this derivative is actually not 0. Does that mean it's not an inflection point? No. I'm just trying to really make it clear the direction is just one way here. So just to be clear, if this is 0, then that means you have an inflection point for sure. But, if you have an inflection point, and maybe you don't know it's an inflection point, it could be the case that the second derivative is not 0. And is there ways to know if you have an inflection point if this doesn't work? I'm afraid the only way to know is by drawing the graph then. So if you can't tell, then the only way you can do this is by drawing the graph. Now in the exam, 90% of the time, 95% of the time, you can tell by looking at this. But some of the time, you can't tell by looking at this. And then they make you have to draw a graph. But they won't say, draw a graph. Now I know there's a lot here, so we'll look at some examples now to see what this means. So just to get us started, I'll ask you to find the turning points for this graph. Okay, so the first thing I want to know is find the stationary points, X and Y. We did this example last week, so it'll take you a minute. Yeah.
What's the difference between turning point and inflection?
Turning point is this point, here and here. That's turning point. And inflection point is this one. These are turning points, and this is an inflection point. Oh, and just to say, in case you're wondering, here, here. The good news is for this side of the notes, if you're wondering, these go in both directions here. So, the second derivative is positive, it's convex. If it's convex, the second derivative is positive. And likewise here, and likewise here, and likewise here. So that's good news. They go in both directions on this side. The only time we could have a problem is only for this side, when they're equal to 0. So you have to be very, very careful when they're equal to 0. You have the 2 points? Yeah. Okay, let's have a look here. So first, before I even start, I should change this into y equals 16 log x plus x squared plus 18x minus 18. The first, thank you. Well, yeah, minus 8, thank you. I suppose it won't matter now because actually when I differentiate, it's gone anyways. Plus 2x plus 18 equals 0. I will multiply by x and divide by 2. So this will be 8 plus x squared plus 9x. I divided by 2 and multiplied by x. So that's 8, 1, 9, 1x. Okay. This looks like it will have nice roots. X plus 8, x plus 1. So we get minus 8 as the first one, or minus 1 as the second one. Right, well this one I think is easy to do in our head because that would be 0, 1, minus 18 is minus 9, minus 25. And then what did we get for this one? Minus 44.7, we'll say.
54.
Oh, 54.7. Okay, thank you. Great. But now, we would like to know if what we have is a maximum or a minimum. Like, this one might be at the top, this one could be at the bottom. We don't know. Is it a max or is it a min? But we can know if we get the second derivative. So if I scroll down a little bit, okay, I'll give you 1 minute again. I want you, well, less than a minute. I want the second derivative. So if you can write that down. And of course, you should remember to change this into x power minus 1 here. Okay, so we'll have minus 16 x minus 2 plus 2, and that's equal to minus 16 over x squared plus 2. Okay.
Stephen,
Yeah.
can you do with that?
No.
Why?
Well, with this one, you could do it after you divide it by 2, because the thing we care about the most is if it's positive or negative, not its actual value. But I would not do it after I've multiplied by x, because we don't know if x is positive or negative. If you have a function which is negative and you multiply it by a negative, then the result is positive. We'll flip the sign around. In other words, you could totally mess up the answer if we did it here. We should do it here, is safest. Okay. Part C. What is the nature of the stationary points? So by that I mean, is it a max or is it a min? Well, if this point was, for example, a max, then the second derivative should be positive or negative. Get some negative, because you want the shape to be concave. If it's a minimum, it should be convex shape, which means the second derivative should be a positive. Let's check. What I'll do next, or what you will do next, take these two answers for x and put them into this here and check if you get a positive or a negative. If you get a positive, then you have this picture. If you get a negative, then you have this picture. Okay, let's see. If I put minus 8 in here, I'll get minus 16 over 64. I'll get something which is positive, so that will make it a minimum. Next, if I put minus 1 in here, I'll get minus 16 over 1, which is minus 16. Minus 16 plus 2 is minus 14. I get a negative, so it's a maximum. Those are the actual values. Oh, sorry, 25 here, thank you. This is a 20. Great. Okay, D. Where is the curve increasing? So how could you figure out where it is increasing? Using derivatives. Which one? Using these points? Something else. Which derivative? First or second? No, first. If I want to know where it's increasing,
So it has to be there.
yeah, where, in other words, where is this positive, then I know it's increasing. Okay, that basically means you need to solve when this here is positive. I'll take a minute to figure that out. We did that earlier in the semester, although we have a little complication that the x is in the denominator. I'll let you think about that. Maybe not as easy as it seems at first. Okay, got an answer? No, not yet. Let's have a look at what we're trying to solve here. So what was it originally? 16 over x plus what? Plus 2x plus 18 equals 0. Okay. So what do I do? Not equals 0 actually. Bigger than 0. Okay, so what do I need to do here to solve this? What do I do next? Multiply by x. But there is a problem if I multiply by x. What might the problem be?
X can't be 0.
Oh well, that's certainly a problem. X can't be 0, but there's another problem.
Can't be 0.
Yeah?
I don't know.
Maybe minus, yeah. If x is minus, then what happens to this?
Smaller.
Smaller.
It turns around, yeah. If x is positive, then it doesn't turn around. So the way we can deal with that, we can do this as two problems. If I scroll down, come on. Yeah, let me just plug this in. Okay. So while this is reopening, how could we deal with if the x is positive or negative? Well, the way I'll deal with it is we look at the two possibilities. So first, let's look at what would happen if x was positive, solve it. Then look at what happened if x is negative, and then solve it. In both cases, you're doing the same thing nearly. So if x is positive, then we can multiply by x and we'll get 16 plus 2x squared plus 18 x bigger than 0. So I get x squared plus 9x plus 9x. Yeah. 9x plus 8 bigger than 0. So I get x plus 8, x plus 1 bigger than 0. It's just minus 1 and minus 8. There's minus 8, there's minus 1. And it's bigger than 0, so that's here and here. So x should be smaller than minus 8 or bigger than minus 1. But we must remember at the very beginning I said x is bigger than 0. So what do we get from this now? Can we use this?
No.
No. Of course not, because we said at the start x is a number bigger than 0. Can we use this?
No.
Kind of, not quite. Part of it, yeah, what part can we use? The bigger than 0 part. Yeah, bigger than 0. Now let's look here. If x is less than 0, everything is the same, right?
Yeah.
Except for what? This gets flipped around. So at the end we get this instead. X plus 8, x plus 1, smaller than 0, good. There's minus 8, there's minus 1. X is smaller than 0. Yes?
Yeah.
So, and we want it to be less than 0, so we want this piece. Can I use both of these? Can I use this? Yeah, I can. This is good. Yeah. So here we actually have two answers. Either x is bigger than 0 or x is between minus 8 and minus 1. Now remember, we have to think all the way back to what we were looking for at the beginning of this question. I want to know, when is this function increasing? It's increasing when x is bigger than 0, and it's increasing between minus 8 and minus 1. If I did this again, except instead of saying increasing I said decreasing, then everything will be opposite. So if it's not increasing, then it's decreasing. Let's try and graph this now. Can I scroll down a little bit? Yeah. Okay, so let's put all our information together. Monica, what were the two turning points we had originally? Minus 8, which I'll put like here. Okay, so I'll just put it like here. I'll just say that's minus 50 there. And was that a max or a min? Minimum. Okay, minimum. Right, what was the second point? Minus 1 and minus 25, so that'd be about here. And what was that? A maximum. Okay, so we know that the shape should look something like this and something like this. Now, x greater than 0 means it's increasing. But let's actually do this one first. Between minus 8 and minus 1 it's increasing. Well, that makes sense. Look at the graph here. It is increasing from minus 8 to minus 1. It's going from a min to a max. So we're happy with that. But it's increasing from 0. So before 0 it was decreasing. So this was heading down. But then when it gets to 0, it's increasing. And it keeps increasing for x always bigger than 0. Yeah. But here, what about to the left of minus 8? Is it increasing or is it decreasing? Well, we said it's increasing between here and here, and it's increasing if x is bigger than 0. So, what do we think? Increasing or decreasing? And remember, this is where we said it's increasing. Well, if I'm here, am I in this? No. If I'm to here, am I in this? No. So am I increasing? No. So I must be decreasing. So this graph must then shoot down. So it's kind of looking quite ugly now, but I think the shape will be like this. It will be flat a little bit here, then increase, and then shoot down, and then shoot back up. This is what I think it will look like. Let's find out. Okay. Y equals, what was it? Log x power 16. Yeah. Like this? Okay, let's see what we get. Now I need to zoom out. I was wrong. So it is actually increasing here. Well, we'll go check now. This part, right. This part, right. This part, right. This part, right. So we were wrong here. So how can we check what it should be? We got a little bit lazy. We should just check by putting in a number. Let's put in -9. See what happens. So I get -16 over 81 plus 2. Is this positive or negative? Positive. So positive means it's increasing. So we should have said that. If I check at -9, I get a positive. So it was increasing then. Huh? Oh yeah, so why didn't I get it here? Here? No, it's still positive. This one here? Ah. Oh! This was our mistake. I'll give you a minute to spot it. When I put these two together, I don't get this. What do I get instead? If I put this and this together, yeah? Opposite? Not quite. X is less than 0, and x should be between -8 and -1. Yeah. Anyways, we won't worry about that because this has gotten way harder than what's in the exam. I've pushed this right up to the limit. You won't get it as quite as difficult as this in the exam. Just before we go on, I just want to finish this by having a look at the, if you look at your workbook, you see there's a box down the bottom there with 9 squares in it. I just want to draw the 9 different possibilities you have. So in the first box, what is it there? The first derivative is negative, and the second derivative is negative. Okay. So if the first derivative is negative, is it increasing or decreasing? Decreasing. And if the second derivative is negative, is it concave or convex? Concave. So it's concave and it's decreasing. What does that look like? Looks like this. going down, and a cave shape. Right, the next one, the first derivative is 0, and the second derivative is negative. So it's still concave, but it's a turning point. So it's actually going to be this part here up the top. The last one is positive, so it's increasing and it's still concave. So that would be this part here. This is increasing and concave. Okay, if we go to the next one, the second derivative is 0, so that means it's an inflection point. And the first derivative is negative, which means it's decreasing. So it's this part here, decreasing. Let me think. Got this right? Okay. This part here. It's decreasing inflection point. I'll skip the middle one for the moment. Next one, inflection point increasing. So that would be like this. Okay, the last one is positive convex, forgot the name, convex and decreasing, convex and decreasing, so that's this one. This one is convex and a turning point, so it looks like this. And the last one is convex and increasing, which is like this. Okay, so the last one I skipped because it's the hardest one. In the very middle, the first derivative is 0 and the second derivative is 0. So does anybody know what shape goes in the middle there for that possibility? What's that? Straight line? No, not necessarily. That is just one possibility, but in general, not only this.
I think so.
You think both?
Yeah.
Like what shape would it look like? Which one? On the left?
Yeah.
Like this one?
No.
This one?
The other is left.
This one? This one?
Yeah. No, down.
There.
Mix of convex and...
Oh, the two at the same time.
Yeah.
Yeah, some kind of mixture between these two.
Yeah.
Good. Not this. Good try though. Anyone else?
Like the one that no net and mean point.
Ah, you mean like something that's kind of like that or something like that? No. Good try. The answer is it could be anything. Yeah. When the first and second derivative are both 0, you have no information about the shape. No information about the shape. This is what I was saying earlier. We have to be careful when they're 0, especially when they're both 0. When they're both 0, we have no information about the shape. 0 information about the shape. So literally it could be any shape. Could be any shape. Yeah. Huh? Yeah, but I could draw you many different functions where the gradient is 0 and it could be any shape that you want nearly. No? You want me? I don't believe me, it's fine. Okay, let me draw that. Guys, I'll show you a couple examples for the non-believers. Yeah. Look, here is my first example. I want you to tell me what is the first derivative? 2x. And this, actually no, let's make it cubed. Okay, what's the first derivative? It's 3x squared. And then the second derivative will be 6x. If x is 0, the first derivative is 0 and the second derivative is 0. Okay? This one. First derivative is 4x cubed and the second one is 12x squared. If x is 0, the first derivative is 0 and the second derivative. So the situation is the same for both. Agreed? They both have the first derivative as 0 and the second derivative as 0. Now let me draw them. The first graph looks like this. The second graph looks like this. In fact, if I did another one, which was minus x power 4, it would look like this. So we could have a minimum, we could have a maximum, we could have an inflection point, we could have anything we want when the first and second derivative are both 0. In other words, we have no information and we could have anything. Now are you a believer? Okay, thank you. No, it's good to doubt. It's good to doubt. Okay, just before we go on, just the very last thing. I know this is very long and it's very difficult. No, wait. Very last thing now. I just need to go back to something earlier. There we go. Oh my goodness. Okay. Okay. Come on. It's getting stuck. I'll just point. Listen, before I give you the questions to try, I just need to correct myself. I told you something which was wrong earlier. I don't want you going home dreaming about it and having nightmares because you realise it's wrong. Alright? This arrow here, I drew it backwards. It's the other way around. Okay? Inflection point means the second derivative is 0. But it doesn't go the other direction. The reason I'm saying this now is because it relates to the point I was just making with KJ with my graph. Okay? So if you can please go to your notes. This arrow is pointing the wrong way and this one's pointing the wrong way. It needs to be flipped around. Now you shouldn't have any nightmares now. Okay? Now look, I know this topic is hard, and it's hard especially if you haven't studied this before. But the thing is, this is one full question in the exam in section B. So it is something you can't really avoid. And it gets worse for the engineering students. Most of semester 2 is this stuff. Yeah. Business students, you have it a little bit easier. Only some of semester 2 is this stuff. Okay, so that's a little bit better for you. Yeah, not as bad as the engineers. Okay, so I'll give you some questions to try for 5 minutes and then you can take a break. It's important that you practice these. So in question 1, can you write these down? 1, A, B, C. In number 2, we'll say C, D, H. Yeah, C, D, H. In number 3, we'll say A, B, O, P.
OP.
Yeah? That's what I said. That's a P. Right. Can you try these for 5 minutes, please? Yep. Question, yes. Correct. No. Inflection. It needs to be like this, and then change to this. Yeah. Inflection is when it changes from convex to concave.
Oh, yes.
Yeah? It's okay? Okay. There's a little bit of vocabulary if you don't have this vocabulary. I think most of you have this vocabulary, but this one we call it global because it's the maximum everywhere.
Yes.
But this one we only call it local because it's only maximum in this area. Yeah. And this one here is local minimum because it's only minimum here. And this graph, it doesn't have a global minimum because this keeps going down. Okay, but I think you know the difference between local and global, these words. But just in case, there's the graph.
I'm sorry, it would be silly. But if I'm doing something and I don't know if it's right.
Yeah. Let's have a look, see. Which one are you doing? Which one's this now? Okay, so, good, okay, so what's your first thing you're doing now?
Frankie?
Not necessary for this one. You can use, do you have your notes from the last class? Is this just maths?
Yeah.
So, if there's a table I gave you, no, it was after this. I don't quite. Oh no, we're back here. Could be here. No, that's okay.
Consider the same, but that's not focused.
Well, it doesn't look like it's in this notebook unless it's. This notebook has an organisation structure to it. The pages seem quite random. No, I have no idea where it is. Do you have your notes from the last class? I just want to show Sarah a table. No, before this one. Yeah. This here. Yeah. I was talking about this table. So for that one there, you need to use. You didn't write it down. Oh, there it is. Oh yeah. Well, that should be in the table, but it doesn't matter. Yeah, you need to use this rule. So you take the power into the front. So the 3 comes into the front to make it a 15, and then reduce it to 2. In other words, take 1 away from the 3. 3 times 5.
Ah.
Yeah. So this will be 15x squared is the answer. Yeah. 15x squared. And then you repeat the process one more time. So you bring the 2 down in front. So 2 multiplies 15. And then you reduce the power by 1. Yeah. So that's, you need, I didn't see this in your notebook, so you need to copy this table down, because you'll need it for today.
Thank you.
Yeah. You forgot how to draw a graph. Which graph are you doing?
I know, but I want to.
Oh! We don't need to draw the graph in number 2. Did I ask you to draw it?
I know, but I want to.
Do you want to use a computer program?
No, I mean, which one actually?
If you would like to, which ones would be good to draw? In the exam, the only graph they've ever asked you to draw that I've seen, no, that's not true. There's 2 types of graphs they ask you to draw. For this lesson. 99% of the time it's a cubic. And then 1% of the time they ask you to draw something like x power 4. Now, we don't do x power 4. The only way to draw that is by making a table. So this is my advice. In the exam, you need to know how to draw quadratics and cubics, sines and cosines. If they ask you something else, then you need to make a table of values. That's the way to do it in the exam. 99% of the time, the worst you get is a cubic. Sometimes you get a quadratic. So if you want to practice, okay, I'd say practice the cubic one I gave you. Now if you want something difficult, like really difficult, maybe too difficult for the exam, you practice a log one.
A log one.
Like these. Now they're very, very difficult. Very, very difficult. More difficult than the exam. But if you want to challenge yourself.
Actually, what
is the turning point? The stationary point? Yeah. Yeah.
Yeah.
Let's see. Have I got all my engineers? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9. 1, 2, 3, 4. I thought we were 9. Am I wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's count to 9 now. I didn't see Jerry, that's what was. You're changed. Good choice. Good choice. And then for business students, we have Victoria and Sammy are in core. And then business students, I'm missing Fahad. Alvin has moved. And who else? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Alvin is 14. Fahad is 16. Wait on, Kedri. No. Wait. I'll tell you when you can go. Okay, now you can go. Unfortunately, the only way to know is from the graph. Yeah. Back already. That was quick. Oh, taking your phone as well. Oh. Nah, you can just take max or min. In the exam, they will only ask you to state if it's local or global if they also ask you to make a graph. I'm only giving you that answer just for your benefit, you know. Okay, take a break for 5 minutes.
Do you want to